Hi, today I'm going to introduce you to Lupine, which is a longitudinal approach to model networks for microbiome data using partial least squares regression. So before we move on to anything else, let me introduce you to what microbiome is. So a microbiome is a collection of different taxa. They can be bacteria, fungi, or viruses that are coexisting interdependently within an ecosystem. So this ecosystem can be your gut, skin, soil, whatever the media you're looking at. So when we look at this microbiome, the most important thing is that these taxa are not independent. So any assumption that you do, like independently, identically distributed, which we normally do in statistics, don't hold in this microbiome data because they are influencing each other. So they can be friends with each other or they can be enemies. So one taxa might help other taxa grow, or it could also decrease the growth of a different taxa. So that's what we mean by coexisting interdependently within an ecosystem. So when we model this, we have to look into these dependencies as well. So when we look at longitudinal microbiome data, this is data that is collected over time. So basically we collect, so if you have individuals or mice, we collect microbiome samples from each individuals across time. And these samples are normally fecal samples. And data generation is done mainly using two techniques, which is 16S rRNA sequencing, which is also referred as amplicon sequencing. So in this situation, we only observe bacteria. And the other one is when you have shotgun metagenomic sequencing, where you observe all the taxa that is living in the sample. So when you look at the 16S amplicon sequencing, I have defined P, N, and T. So the P is the number of taxa. So if you're looking at it in a statistical point of view, this is the number of variables you have in your data. N is the number of samples you have. T is the time points. So you could say that the P is around 500 to 1,000. The sample size is 50 to 100, and that's a really big sample. So normally we would have just 10 samples, or even sometimes it's just 3 samples. And T is the number of time points. So we normally have a very shorter period of time. So especially if you're doing mice studies, so the time points are very, very short because you are doing a controlled experiments on mice. So normally it's not years. But if you're doing a more observational kind of studies on human, then they can be longer in time points. And when you look at these two data generating methods, you can see the only difference or the main difference is the P, or the number of variables, or the number of taxa in metagenomic sequencing. So you have a lot more number of variables when you do a shotgun metagenomic sequencing. But I'm going to apply Lupine into 16S rRNA sequencing as case studies, but the idea is pretty similar. So you could also use this method on shotgun metagenomic sequences as well. So before we move on to anything about the method itself, I also wanted to highlight some special characteristics from in our data. So as I mentioned, we're analyzing longitudinal microbiome data. So as the name suggests, there's two parts that come into play. One is the longitudinal aspect of the data, and the other one is the microbiome. So when you look at the longitudinal aspect of the data, you have the time trends, and also you have the within subject correlation. So what we mean by time trend is that there could be some increase in trends in some species or taxa, and you could have different across different time points. And also we have within subject correlation. What we mean by here is that we observe the same individual or the same mice across time. So if you're looking at individual, so they would have the similar diet, they would be taking the same medication. So when you look at across time, there would be some correlation happening across time because it's the same individual. And when we go into the microbiome, the first data characteristic is sparsity. So what we mean by sparsity is there's a lot of zeros in your data. So I have given a snapshot of my data in this table. So it basically has the taxas in columns and your samples in the rows. So you could see how these counts vary across samples as well as across taxa, and you see a lot of zeros in some of the taxa. So that's why we mean by sparsity. And also we have over dispersion. So that means the mean and the variance is not very equal. So any assumption on that the variance and the mean is equal, like in a Poisson distribution, might not be valid in this kind of data. And also there's also high intersubject variability. So across time, we have within subject correlation. But if you look at two individuals, there's going to be a lot of variability. Again, this is due to they might be living in different environments, they might be consuming different foods. So all these add up, and then there's all this variability that is happening inter-subject in our data set. And also it's multivariate, so the taxa are not independent of each other, so one could influence the other. So you have this multivariate kind of response. And high dimensional, because we have a lot of number of taxa in our sample. And maybe the most challenging part of this data is the compositional nature. So what we mean by compositional nature is that the observed counts are not actually actual counts, they are relative counts. So when we do microbiome samples, you always have this total read counts, or referred to as the library size, and these all these counts are actually relative to the library size. So if you have a smaller library size, there's a bigger chance of having zeros for the low abundant taxa. So this is a bit different from ecological data sets where you observe a species in the nature and there are actual observations, whereas this is actually a relative count. So it's relative to the library size you observe. So if you want to learn more about longitudinal microbiome data characteristics, so you could refer back to this review we did in 2022 and have a read through that paper, so you could get a bit more understanding or some more deep explanations on each of these categories will be found there. And also in this figure, I have given few examples of different taxa, and you can here again see that some taxa there's like very low abundance, and for some time points, for a specific individual, there's a high count. So this is what I mean by high inter subject variability. And also within like across different taxa, you could see the patterns are bit different. So then there's no rule, or there's no consistent pattern across observed across majority of the taxa. So they're going to behave in different ways, but it does not mean that they are independent of each other. There is some interdependency that's happening behind the scene that we are not being able to see. So the idea of networks or modeling microbiome networks is to infer these associations. So basically, like if you forget about the longitudinal aspect, the basic idea is that we want to get this network that could tell us that which taxa are associated with each other. So basically, like if one increases, is there another taxa that is increasing with that taxa? That kind of a question. So in longitudinal microbiome, so the objectives of getting these networks is to understand these associations between different microorganisms, and also to identify the important members of a microbial community. So you want to identify which taxa or microbes are highly connected with other taxa. And also we want to see if interventions such as an antibiotic or a dietary change is happening in these individuals, how these associations or how these connections between taxa are changed. So these kind of objectives are the main reason that we want to infer these microbial networks. So when we look at these associations, so if you're in a more statistical kind of a setting, the most common approach to model these association is using correlation kind of analysis. So basically you could do Pearson correlations, PMN correlation, kind of a correlation calculation to find these associations. But when we look at microbiome, it's not that straightforward due to its characteristics. So I have kind of explained a few of here. So for example, if you take sparsity, which is zeros in your data, so when you have zeros, you actually don't know whether these zeros are actual absences or whether they are undersampling. So if your library size is small, so sometimes because that library size is low, you might have a lot of zeros in the low abundant taxa, but it does not necessarily mean that it's not there. So what happens is that when you have these matching zeros, for example, I have in these two tables, I have given example. So if you look at the first table, so you have two taxa, and if you calculate the correlation coefficient, Pearson correlation coefficient, it's around 0.11. So the same data, I just added few columns of zeros, and you see that how the correlation is increased to 0.61. So this increase is actually a valid increase if they were actual absences. But you don't really know if these absences are actual or whether they are due to undersampling. So that's why there could be, or there in most cases, there will be inflated correlation values due to these matching zeros. Another problem is compositionality. So as I mentioned before, we have relative counts rather than absolute counts. So in these situations, in theory, people have shown that Pearson kind of correlations are not to be used because they're not suitable for compositional data analysis. So we have this problem that we can't use the traditional correlation method. So the first thing is to look at what people have done in single time point analysis. So people have developed several microbial inferences methods for single time point data. So the main there are two branches in when you look at these network approaches. So one looks at correlation based methods, another would be a partial correlation or precision based methods. So I have given two examples, sparse-CC and speak-EC, for each of these approaches. There are newer approaches, but they also would fall into these, mainly into these two categories. So I'm going to use these two methods because they're widely used across different, even today, people are using these methods. So I'm going to benchmark my method against these two methods. Okay, so what is the difference between going into a correlation-based method versus a precision-based method? To show that, I have created a simulated data set here. So in my true network, I have 100 edges. So each of the edges means that there's a connection between these two taxa. So if there's a connection, you will have a link between the two nodes. So the nodes here are the taxa, and edges is the association between the taxa. So we basically have 100 edges here. So what happens when you use a sparsity or like a correlation based method is that you are tend to pick up more edges, but there are also going to be a lot of false edges. This is happening because there could be indirect correlations that are being captured if you're using correlation. So basically, if A, B and C are correlated with each other, because if, for example, if A is correlated with C and A is correlated with B, C and B will also be correlated just because A is correlated with both of them. So it's basically in correlation, you would pick out indirect correlations. Whereas when you go into precision kind of a measure, it looks at direct correlation. So it kind of tries to avoid getting indirect correlation. So that's the basic idea. And you can see that even in this simple example. So if you use peak AC, you get 39 true edges. So it's a bit lower than 53, but you can see the false edges are drastically reduced from 78 to 26. So that's what you get. So there's a trade-off. So if you are using a correlation-based method, you will get a lot of these edges identified, but also you will have equally many false edges. Whereas when you use precision-based method, there will be fewer edges you find, but they will be much more likely to be correct. So you have to identify what type of a, approach you want. Do you want high sensitivity or you want high precision? So correlation methods are more spurious associations. So they could give you low precision, but they identify more connections. So you have high sensitivity. So there's always this trade-off between sensitivity and precision. So now we will move on to the longitudinal approach. So in this approach, what my main idea is whether we can use the past data to influence our network. But we also don't want these networks to influence too much. Like, we don't want the past to influence our current network too much because there could be network disruptions at specific time points. So we want to learn from the past, but we also don't want to learn too much. So I developed Lupine, which is a very simple idea. So if you look at the ideas, the first one is that I wanted to go in the direction of partial correlation. So when you want to find the partial correlation, so for example, let's say we have two taxa, A and B. And if you want to find the partial correlation between A and B, given that you have another taxa called U, so how you can get this partial correlation, the easiest way is you could do a linear regression. So basically what you do here is you do a linear regression on A with U as your independent variable. And again, you do a linear regression, B as the response, and then again considering U as your independent variable. And after fitting these two linear regression models, what you do is you calculate the residuals, which is the EA and EB, and then you use these two residuals to calculate the correlation. So you basically calculate the correlation between two residuals, and this would be equal to the partial correlation between A and B. So if you mimic the same idea, so for example, in this matrix where my columns are the taxa, n is the samples or the rows are the samples. So for now, let's forget about a longitudinal part. So let's just assume that we only have single time point data. So in that case, you just have this one X matrix. And let's say that our main objective is finding the correlation or the partial correlation between the ith taxa and the jth taxa. So what you have to do based on what I explained before about partial correlation is you basically have to run two regression models on xi, excluding I and j. So you basically have to regress xi on all other taxa other than I and j. So you basically regress this column across all these green columns and xj again across all these green columns, and then you get the residuals, and then you find the partial correlation for I and j taxa. And then you can do this repeatedly for all pairwise comparisons in our data. But the problem here is that you have a lot of variables. So for example, if you remember the dimensions, so normally like if we have enough samples, then n would be 50, but xj can be like 100 or 200. So in these kind of situations, simple linear regression or like multiple linear regression would not work well because you have a lot of variables in your model, but you would just have fewer samples. So the simple multiple linear regression would not work in this situation. So that's where the second step comes in. So in the second step, what we do is instead of regressing everything across all these variables or all those green columns, we are going to get a low dimensional representation of all those green columns. So if you look at just one single time points, how you can get the low dimensional representation of a data would be a principal component. So you use the first principal component as the low dimensional representation of your controlled taxa. So the control taxa is any taxa that is not I and j, because we are interested in finding the partial correlation of I and j. So what happens? So the same idea can be extended when you have multiple time points. So for example, if you have 2 time points, what I do is I get a low dimensional approximation of this control taxa, and then I use that low dimensional approximation to find the partial correlation. So basically, I use this partial least squares regression to reduce my dimension and then use this U column in my previous linear regression in here. So instead of using this full matrix in here, what I'm going to use is just a dimensional reduction of that matrix. So basically, at a given time point, I'm just going to use UT instead of the full matrix. So in 2 time points, how do I get the low dimensional representation of control variables is using partial least squares regression. So if you have more than 2 time points, so it's basically an extension of PLS, which is referred as block PLS. So, and I use this technique to get my low dimensional representation. So basically what I do is I take 2 taxa at a time, and then I take the low dimensional representation of the control taxa control variables, and I use that low dimensional representation in my regression to calculate my partial correlation. So that's basically the idea. So the idea is very similar to principal component regression, where you use the principal components as your independent variables in your regression. So it's the same idea, but a bit of it's different for when you look at 2 time points or multiple time points. Okay, so that will give me networks at each time points. For example, if you have like 5 time points, at the second time point, I will use the first time point information, and then I would get the network, and I would do this sequentially across all time points. So basically, you will have set of networks across time. That's great. So when you have several networks across time, how do you compare these networks? So I will give you a simple example here. So let's say we just have 3 time points, and these 3 time points generated this kind of different networks. So this is the results from Lupine, but how do you then use these Lupine results to compare networks or identify differences in these networks or identify taxa or nodes that are important in these networks? So basically, how do we compare the networks? So the idea would be you could look at them graphically or visually, like you could plot them and then compare them, but it's going to be a bit harder when you have 200, 300 nodes in your network to compare them across 10 different time points. So we need several measures to compare them. So now I'm going to explain how I use 2 different measures to compare my inferred networks from Lupine. So the first one is the structured base distances using GDD. So GDD stands for graph diffusion distance. So this kind of looks at the similarity based on information flow and connectivity. So are they very similar in the connections based on how information would flow across these networks? And how to compare them. So if you have a GDD very distance very small, that means they're very similar. So in this B1 figure, I give you the GDD values or pairwise distances between these networks in this here, and you can see in the diagonal you have 0 because when you compare the same network with itself, you see the distance is 0. And if they're very similar, you see that you have a smaller value. So in these networks, these black lines means the difference from the previous time point. So at time point 2, you have these 2 new connections. At time point 3, you have these 4 new connections from time point 2. So you could see that when you compare these pairwise distances, you see that the maximum distance is between time point 1 and time point 3. Okay, so you get these pairwise distances. Again, this is great, but if you have 10 networks, you will have a 10 by 10 matrix. And again, if you have more networks, there will be a lot of pairwise distances. So it's again not easy to compare, like if you want to find very different networks across time. So what we do next is that using these pairwise distances, we map them into a multi-dimensional scaling. So basically we project them into a low dimension. So these pairwise distances are projected into a low dimensional distances, and you can see that from T1 and T2 is much more similar compared to T3. So if the networks are far apart in this plot here, it means they're very dissimilar, and if they're close to each other, that means they are very closely in the network itself. So you can say that T3 is a bit different from T1 and T3 because they have the maximum distance between the three networks. So that's one way. This would tell us any network is very different from other networks. But it again does not tell us which taxa or which nodes that might be causing these big changes. So it's another thing that biologists would be interested, because you want to find out what's happening at the node level, or what is these nodes that are different across these networks. So that's the where we have the second measure, which is a IVI score. So this is an integrated value based on 3 measures: local measure like degree centrality and cluster rank, semi-local measures such as neighborhood connectivity and local edge index, and global measures like between centrality and collective influence. So it kind of uses these several network measures, and it integrates all these measures into one value for each node. So higher the value, higher it means to high likely that that node will be highly influential. So in here, I have shown the IVI values for each node in each of the networks. And what we can see is that the node O is very influential. So the node O is the one that was very connected to all the other nodes, is very influential across 3 time points. And what is also interesting is that F is becoming influential, is much more influential at time point 3. So at time point 3, F is starting to be a influential node. Again, so this PCA will give us all, like if you have 100 sorry, this heat map will give you like how many nodes you have. So basically how many taxa you have as columns, and you in the rows you will have the time points. Again, this is a good thing, but you also want to see, based on this node influence, how is my network similarity compare. So for that, what you can do is you can use these IVI scores and then use that in a PCA to try to identify which networks are similar based on these IVI scores. So again, you see a similar inference from the previous plot, even in the PCA. So you see that T3 is far apart from T1 and T2. So basically, in the first principal component, we can distinguish T3 from the other 2 networks. So that's how I have compared the networks across different time points. Okay, so that's all the things that are on the theoretical side, or all the explanations on the method. Now we will see how the method works on simulated data. So when you look at the simulation study, so I'll explain the simulation study first. So in the simulation study, so how did we simulate? So for simulation, I used a real case study to generate two different networks using speakeasy method. So basically, I used real data and inferred two networks that I could use in my simulation. And using these two networks, then I generated data across time. So basically, in my simulation, I have 10 time points, and I assume from time 1 to time 5, I have network 1, and from time 6 to time 10, the data is generated from network 2. So there's a network change at from day 6 onwards. And how the data are generated is using a multivariate Poisson distribution, using a copula method. And it's basically a very simple idea again. So what we do is you have a very a multivariate Poisson distribution where the data is generated. Also, to have some dependency across time, we have introduced something called this thinning operator, which basically takes the previous time points counts and thins them so that you can consider them as deaths or survivals. So you basically have counts of different taxa in the previous time points, and they will be reduced in the current time point. And also you will have new taxa that is being added. So these are more like birth and death. So you basically reduce the counts, assuming that there's some taxa that was alive at the previous time point that are going to die during the current time point, and also some new births based on a multivariate Poisson. So in the simulation, I simulated 50 data sets with n equals 23, which is a smallest sample size, and n is equal to 120. So in all these 50 data sets, my p, or the number of taxa, is set to 54, and the number of time points is 10. And let's look at the results now for the um, n equals 23. Okay, so n equals 23 is this result. So what we see here is that I have looked at two measures, the area under the curve for ROC, or the receiver operator characteristic curve, or also the area under the precision recall curve. So basically we want higher values for both of these measures, and higher the value is better model performance. So what we can observe when the sample size is smaller is that the Lupine single version is that when we don't use any past information, and also Lupine, the darker pink one, is when we use the past information. So what we observe here is that Lupine is doing a good job similar to sparse CC, which is a correlation-based method. So recall that Lupine is a partial correlation method, but it's still doing a similar job as sparse CC. But it is better, or like it's computationally efficient than sparse CC, because it's a bit faster than sparse CC, like 3 times faster. And also what we can see is the lowest ROC values are observed in speakeasy. And for the precision recall curve, I think the results are very similar across all the methods. And that's what we observe when n is equal to 23. But when we increase the number or the sample size, what we see is that actually the two Lupine methods gain more PRC, or the precision recall curve. So we have a much more higher precision recall curve than sparse CC, and we also have a similar sensitivity and specificity, or the receiver operator curve is having a much more higher area under the curve, similar to sparse CC and higher than the speakeasy. So what we see is that we get a better sensitivity in using lupine and also a better precision. So that's a good thing. So we have doing better in both the ends. So if you're comparing the ROC curve, you can see that lupine and sparse-CC are doing good. And if you go into the precision recall curve, what we see is that lupine and speakeasy is doing a good job. So overall, lupine is doing a good job. So this is again based on simulated data. I will show some advances of using lupine over lupine single using a case study. So the first case study is a high-fat, high-sugar diet case study where we use, which is a case control mouse study. So in this study, what we observe is two groups. So you have a set of mice that is having a normal diet and another set of mice consuming a high-fat, high-sugar diet. So what is done in this experiment is that you take fecal samples from each of these mice across 0, 1, 4, and 7. So these are the days that the fecal samples are collected and then they are analyzed. So after removing the low abundant taxa across these two groups, we are left with 212 taxa. So basically in our networks, we will have 212 nodes. So using Lupine, these are the networks that we get. So when I mean lupine, it's the longitudinal aspect or the longitudinal approach. So what we see is that we see a lot of connections happening across both the two diets. But what we observe is that connections in bacteroidals is decreased in the high fat, high sugar diet. So these are represented in green. So you could see there are a high number of connections, green connections, or the green dots are much more bigger, or they have more nodes connecting with other nodes in the normal diet compared to the high fat, high sugar diet. Also, we say that the connections of clostridials is increased in the high fat, high sugar diet as observed here. So that's what we observe. So we see some connections increasing and we see some connections decreasing, but it's really hard to find causal inferences or inferences to back these claims because these are just basically based on associations. But we find similar ideas, or we see that there are several papers that talk about decreased relative abundance in bacteroidals, and we also see enrichment of lactobacillus. So these are some key findings that were found in previous research and also agrees with the number of connections. So maybe higher the connections, there's going to be higher that they are more abundant. So again, we can then compare how these networks compare with each other. So if you use the GDD or graph diffusion distance, and if you look at the networks, what we see is that there's a kind of a clear grouping patterns in the normal diet group. So basically across all these three time points, 1, 4, and 7, the normal diet group kind of has a close cluster, whereas the high fat, high sugar diet have this kind of a transition phase where the day one is very different from the later days. And the similar kind of clustering pattern also can be seen in the IVI scores. So if you do a PCA on the IVI scores, you again see this kind of a consistent pattern. So again, it gives you some kind of a consistent results through using different measures. What happens if we use lupine as well as lupine single? So this plots are the first two, the top plots are from lupine single, whereas the bottom plots are from lupine. So you can see when you look at lupine single, the results between these two measures are not that consistent. But we see very consistent results when we use lupine, especially when we use like mouse studies where the experiment is more controlled than human studies where there's a lot of variability happening. So I will explain these in other case studies that I'm going to show next. So the second case study is the VRE-FM case study. This is an intervention study, but again on mouse. So when we do mouse experiments, they're more controlled because we have all the control over these mice. And this, again, remember, a mouse study. So in this experiment, you don't have two groups, but you have different phases in the time frame. So for example, from day 0 to 5 is the naive phase, where they're kind of in a stable kind of a space. And then on day 6 and day 7, they're given an antibiotic. And on day 9, they are again being infected with this VRE-FM, or vancomycin resistant enterococci fecum, which is like a common pathogen that you find in hospitals. So the mouse are being infected with this on day 9. And then you also observe how the networks are, or we observe the fecal samples on day 12, day 13, and 14. So you basically have interventions on 6 and 7 from the antibiotic, and also on day 9 from the VRE-FM colonization. So after you filter the low abundant taxa, what you are left with is around 126 taxa in this case. So if you want to read more about the experiment itself, so you can refer to this paper that is given below. So when we compare the networks across time, we see a clear difference between the naive phase and the other two phases, which is antibiotic and VRA, which is kind of expected because in the antibiotic phase, we observe a lot of uh, taxa to be reduced because of the antibiotic effect. And you see that, and you again see a very consistent pattern between the GDD MDS plot and also the IVI PCA plot. And it's also nice to see this kind of trajectory where you kind of see that on day 9, there's a bit of a difference because this is where the VRE is being administered. And again, you see this kind of a clear grouping in the later stages of the experiment. So you could kind of see that transition from day 9 to the later dates. You can also look at the IVI values across different taxa. So in here, each of these sub-figures are for different or taxonomy order, and each of the line is different taxa. So you could say that, in the green phase, which is the naive phase, you see a lot of connections in these clostridoids, and you see that after the antibiotic, the clostridoids connections, or the IVI values, are actually drastically reduced, and it's also not even recovered till the last part of the experiment. But if you look at the bacteroides, which is in green, you see that during the antibiotic phase, it's decreased, but it seems to be picking up the IVI values at the later stage. And also you see an increase in lactobacillus in the VRE-FM stage, and this is expected because VRE-FM is actually what we are been colonizing is actually belong to this lactobacillus group. So we expect to see this kind of increase in this group because we are infecting the mice with that taxonomic order. And the final study is a diet study, but it's on humans. So you observe a little bit of much variability than in mouse studies because we have a less control over this kind of human studies. Again, this is an intervention study, but it also has two groups. So what happens in this experiment is that you have this baseline period where 20 individuals basically have a similar diet, and then from day 0 to day 5, they have 10 individuals follow a plant diet, and another 10 individuals would follow an animal diet, and then they would follow for another 5 days, which is a wean-off period where they're kind of looking at the effect when they kind of get into a much more balanced diet, or not a very restricted plant diet or animal diet. So looking at this experiment, if you do a filtering, you are left with around 311 taxa after removing for the low abundant taxa. And again, if we compare the different networks across the two measures, what we see is that we don't see the um, very similar kind of plots as we saw in mouse studies, which is expected because we having human studies here, which is there's going to be a lot of variability. But still, there's some agreement in these two plots. For example, in here, we see that there's a clear grouping pattern in the animal networks where the intervention is happening, and also the earlier stages of wean off is grouped together, and the later stages of wean off and the start of experiment is grouped together. And you see this day 6 standing in between these two clusters. You can again see a similar kind of thing here, but it's not that obvious. So it's more like they're much more closer than the two clusters here. But what we see, the commonality between these two plots is that you see a lot of variability in the animal networks compared to the plant-based networks. And another interesting thing we see in this IVI scores, which is looking at the influence of different taxa, what we see is that at the start of the experiment, you see a clear grouping of these naive or the baseline networks, which is expected because at the start we assume that these nodes or taxa would have similar influence regardless of which group, because they're being given the same type of diet. And after you give them the two interventions, you see that they kind of starts to vary a little bit. So this again gives us little information about how the networks are grouping. But again, all of this let us compare networks, but we need more approaches to validate these kind of associations to go into more kind of a causal kind of an inference. Right now, we're just making inferences on associations. So in this presentation, I have gone through the characteristics of longitudinal microbiome data. Then I also explained Lupine, which is a new method for analyzing longitudinal microbiome data to get the networks. And then we looked at how we can compare the inferred networks from Lupine using two measures, GDD and IVI. So the GDD basically looks at globally how the networks compare to each other, whereas IVI looks at the node-wise influence and then how it compares with different networks. And through simulation, we showed that how Lupine is doing a good job compared to single time point methods. And also we applied Lupine into 3 case studies, and we demonstrated that we can extract meaningful information from this approach. And finally, I would like to thank Likao Lab. You see our group here, and these set of people have helped me to make this project a reality, and I would like to thank them wholeheartedly. And you can see my email address down here. So if you have any questions regarding the method, please email me, and I'll be happy to take any question. Thank you.